Think you know the whole story? Turns out you were probably taught the half-truth. Welcome to Half-Truths. Close your eyes for a second and picture your middle school science classroom. Remember the smell of chalk dust, the slightly sticky linoleum floor, and that one poster of the solar system that was definitely from the 1980s. The teacher, trying to make planetary physics cool, wheels out a globe. They give it a spin and then tell you something that blows your 10-year-old mind. Something that makes you feel connected to the entire planet every time you wash your hands or flush the toilet. They tell you that right here, where we are, water drains out of a sink in one direction. Let's say, clockwise. But if you were to magically transport to Australia, that same sink would drain the other way, counterclockwise. Why? Because of the rotation of the Earth itself. A force so immense, so powerful, that it reaches into every home, every bathroom, every kitchen, and dictates the direction of every single swirl of water. It's called the Coriolis effect, and it feels like a secret handshake with the universe. It's the kind of fact you'd share at the dinner table, feeling impossibly smart. It's elegant, it's symmetrical, and it's one of the first times many of us feel like we can see the grand, invisible forces of the cosmos at play in our everyday lives. It's a fantastic story. It connects the mundane to the magnificent. It turns a simple drain into a planetary compass. But what if that story isn't the whole story? What if that satisfying, perfectly symmetrical piece of scientific trivia that we've all heard, the one repeated in movies, TV shows, and by countless science teachers, is actually a half-truth? Today, we're putting on our detective hats and our plumbing gear. We're going down the drain to investigate the great Coriolis conspiracy and figure out if the spin of our planet truly has any say in the spin of your sink. The story we all know is as simple as it is captivating. It goes like this. The Earth is a spinning sphere. We're all hurtling through space on this giant rock, rotating at a blistering speed of over 1,000 miles per hour at the equator. But because we're moving with it, we don't feel it. However, this rotation has a subtle but profound effect on anything that moves freely across the planet's surface, like air, water, or even long-range missiles. This deflection is the Coriolis effect, named after the 19th century French engineer and mathematician Gaspard Gustave de Coriolis. The common explanation uses the analogy of a merry-go-round. Imagine you're standing at the center of a spinning merry-go-round, and you try to throw a ball to your friend standing on the edge. From your perspective, you threw it straight. But because your friend was moving while the ball was in the air, the ball will appear to curve and land behind them. That apparent curve is analogous to the Coriolis effect. Now, apply that to the Earth. In the northern hemisphere, this effect causes moving objects to be deflected to the right. In the southern hemisphere, they're deflected to the left. This is where the bathtub comes in. The story says that as water starts moving toward the drain, the Earth's rotation exerts its influence. In the north, the water gets a tiny persistent nudge to the right, creating a clockwise vortex. In the south, it gets nudged to the left, resulting in a counterclockwise spin. At the equator, where the rotational forces are perfectly balanced, the water should, theoretically, drain straight down with no spin at all. It's a beautiful piece of physics, a perfect demonstration of a global phenomenon in a local setting. And why wouldn't we believe it? It makes intuitive sense. We see giant, swirling weather patterns on the news. Hurricanes in the northern hemisphere, like Katrina or Sandy, spin counterclockwise. Typhoons in the southern hemisphere, like Yasi, spin clockwise. Wait, hold on. Hurricanes spin counterclockwise in the north, but I thought the story was that sinks spin clockwise. That's odd. Let's put a pin in that for a moment. Despite that little inconsistency, the core idea is the same. A big spin on a big ball causes a little spin in a little basin. The logic seems to flow as smoothly as the water it describes. This idea is so pervasive that it has become a staple in popular culture. It was famously featured in an episode of The Simpsons where Bart makes a collect call to Australia to ask which way the water drains, leading to a massive international incident. It's been a plot point in movies and a fun fact in countless articles and books. It's also become a live tourist attraction. Travelers visiting countries on the equator, like Ecuador or Kenya, are often treated to a roadside demonstration. A local guide will stand with a portable basin of water right on the equatorial line. First, they'll place it a few feet into the northern hemisphere, pull the plug, and drop a few leaves in. The water swirls and the leaves dutifully follow a clockwise path. Then, they'll pick up the whole setup, walk a few feet across the line into the southern hemisphere, and repeat the process. Like magic, the water now drains counterclockwise. And for the grand finale, they place the basin directly on the equator, and the water drains straight down, no spin at all. It's compelling, visual proof. Case closed, right? The science is sound, the demonstration is clear. The myth, it seems, is a fact. But that's the thing about a good story. Sometimes it's so good that we don't want to look too closely at the details. We don't want to pull at the loose threads for fear the whole beautiful tapestry might unravel. But that's exactly what we're here to do. Let's go back to that little inconsistency we noticed earlier. Hurricanes. In the northern hemisphere, hurricanes, cyclones, and other large low-pressure systems spin counterclockwise. But the myth about sinks often claims the water should spin clockwise. Why the contradiction? Already, the perfect symmetry of the story is starting to wobble. Some versions of the myth get it right, claiming a counterclockwise spin in the north, but the very existence of this confusion is our first clue that something is amiss. The next thread to pull is a question of scale. The Coriolis effect is undeniably real. It dictates the paths of ocean currents and the jet stream. It has to be calculated for long-range artillery shells and sniper shots. A missile fired 1,000 miles will be deflected by several miles if you don't account for it. So the force is there. But think about the difference in scale. A hurricane can be hundreds of miles wide, and the air within it travels for days over vast distances. An ocean current flows for thousands of miles. A sink, on the other hand, is maybe 1.5 feet across. The water in it moves for a few seconds over a distance of inches. Is it really plausible that the same force governs both phenomena with such visible effects? It's like saying that the gentle gravitational pull of Jupiter, which can sling comets across the solar system, is also responsible for you tripping on the sidewalk. While technically true that Jupiter is pulling on you, its effect is so infinitesimally small compared to the Earth's gravity that it's completely irrelevant. This is where we have to look at the numbers. Physicists have calculated the strength of the Coriolis acceleration on a draining body of water. The result? It is astonishingly, ridiculously tiny. The force is about 10 million times weaker than the force of gravity. It is so weak that any number of other, more immediate factors will completely overwhelm it. The shape of the sink basin is a huge one. Is it perfectly symmetrical? Is the drain perfectly centered? Are there any small nicks or scratches on the surface? The slightest imperfection will create a bias in one direction. Then there's the biggest culprit of all, residual motion. The water in your sink is never perfectly still when you pull the plug. The very act of filling it, the direction the faucet was pointing, the swirl of your hand as you washed it, or just tiny imperceptible movements in the water create a slight angular momentum. This pre-existing motion, however small, is many, many orders of magnitude more powerful than the Coriolis effect in that context. You can easily prove this yourself. Fill a sink, let it drain, and observe the direction. Then, fill it again, give it a gentle stir in the opposite direction before pulling the plug, and watch as it drains the way you told it to. You, with a flick of your wrist, have just overpowered a force generated by the rotation of the entire planet. So if the effect is too weak to be seen, what about those convincing demonstrations at the equator? That, my friends, is where science gives way to showmanship. The trick is a classic piece of misdirection. The demonstrator isn't showing you the Coriolis effect. They are creating it. When they pour the water into the basin, they do it with a slight, almost unnoticeable angle. On the northern side, they pour it to create a subtle clockwise current. On the southern side, they pour it to create a counterclockwise one. For the grand finale on the equator, they pour it carefully and directly into the center, creating no initial spin. The shape of the basin they use is also often specially designed to be perfectly symmetrical, to reduce any other variables and make their subtle influence more effective. They are not demonstrating a law of physics. They are demonstrating a principle of fluid dynamics that they are cleverly manipulating. It's a magic trick disguised as a science lesson. The origin of this myth is a bit murky, but it seems to have solidified in the public consciousness around the mid-20th century. It's a classic case of what happens when a real complex scientific principle is oversimplified for popular consumption. The Coriolis effect is real. Its effect on large-scale systems is real, but somewhere along the line, in a textbook, a science documentary, or a classroom, the desire for a simple, relatable example took over. The sink became the go-to analogy, and the analogy eventually became accepted as a literal fact. It was a story too good to check. It provides a tangible link to an invisible force, making us feel a part of the grand cosmic dance. But the truth, as it often is both less magical and far more interesting. So let's drain away the myth and fill the basin with the real story. The direction water spins down your drain has absolutely nothing to do with which hemisphere you're in. It is determined by local, immediate, and much more powerful forces. The primary factor, as we've touched on, is the initial motion of the water. Any pre-existing swirl, no matter how slight, will dictate the final vortex. If you could create a perfectly circular basin with a drain exactly at the center and fill it with perfectly still water, and then manage to remove the plug without disturbing the water in any way, a feat that requires laboratory conditions, then, and only then, would the Coriolis effect have a chance to show its face. In fact, this exact experiment was done. In 1962, a scientist named Asher Shapiro, wanting to settle the question once and for all, conducted a meticulously designed experiment at MIT. He used a massive 6-foot diameter circular tank with a small drain hole in the center. He covered the tank with a plastic lid to prevent air currents from disturbing the water, and he let the water sit for 24 hours to ensure all residual motion had died down. When he finally, carefully, pulled the plug from below, he observed a very slow, very slight counterclockwise rotation, exactly as predicted by the Coriolis effect for the northern hemisphere. But it took nearly 20 minutes for the vortex to even become visible. This wasn't a rushing, gurgling drain. It was a ghost of a rotation, a whisper of a force finally making itself heard in the absolute quiet. So, yes, the effect is there. But unless you plan on waiting a day for your bathtub to drain under laboratory-controlled conditions, you're not going to see it. The other major factor, especially in toilets, is engineering. The direction a toilet flushes is not left to chance or planetary physics. It is deliberately designed by the manufacturer. The water jets under the rim are angled to create an efficient, powerful, and predictable swirl to clean the bowl. That swirl is a product of clever plumbing, not cosmic alignment. If you buy a toilet from an American company, it will likely swirl one way. If you install that same toilet in a house in New Zealand, it will swirl in the exact same direction. The toilet doesn't know where it is. It only knows how it was built. The real aha moment isn't that the myth is wrong, but that the reality is so much grander. We were looking for evidence of the Earth's power in the wrong place. The Coriolis effect is not a subtle parlor trick force. It is a world-shaping powerhouse. We don't see it in our sinks, because our sinks are too small for its stage. To see the true work of the Coriolis effect, you have to zoom out, way out. Look at a satellite map of the Earth. Those majestic, swirling cloud formations of hurricanes and typhoons are the true signature of the Coriolis force. As air rushes from high-pressure areas to low-pressure areas to form a storm, the Earth's rotation deflects that moving air. In the northern hemisphere, the air is deflected to the right. This causes the entire system, which can be larger than a country, to rotate counterclockwise. In the southern hemisphere, the deflection is to the left, resulting in a clockwise rotation. There's that word again, clockwise. The confusion from the myth often gets the directions backwards, but the weather patterns are the undeniable proof. This is not a subtle effect. It is the fundamental organizing principle of our planet's weather. It also governs the great ocean currents, the massive, slow-moving rivers within the sea that circulate heat around the globe and define our climate. The North Atlantic Gyre, a massive system of rotating ocean currents, circulates in a clockwise direction, thanks to the Coriolis effect pushing the water to the right. Its counterpart in the South Atlantic spins counterclockwise. These gyres are the planet's circulatory system, and they are steered by the same force we mistakenly attributed to our plumbing. This is where the power lies. Not in a tiny vortex that lasts for 5 seconds, but in colossal, millennia-old systems of wind and water that make life on Earth possible. The half-truth gave us a neat but trivial anecdote. The whole truth gives us a profound understanding of the engine that drives our planet's climate. We've traveled from a simple classroom fact to the heart of planetary dynamics. We started with the appealingly simple idea that the Earth's spin choreographs the water in our drains, a symmetrical dance between the hemispheres. We saw how this story is so compelling, reinforced by pop culture and even clever roadside tricksters at the equator. But when we pulled on that thread, the story unraveled. We found that the force in question, the Coriolis effect, is far too weak to have any say in such a small and fast event. We learned that the real directors of that show are mundane things like the shape of the basin and any tiny leftover currents in the water. But in losing the myth, we found a much better truth. The real story of the Coriolis effect isn't about bathrooms. It's about the very breath and blood of our world. It's written in the spiral arms of hurricanes, the vast circular paths of ocean currents, and the prevailing winds that shaped human history. Correcting this half-truth matters because it teaches us a critical lesson about scale. It reminds us that not all scientific principles apply equally in all situations. It shows how an elegant analogy, when stretched too far, can warp into a persistent falsehood. We trade a quirky bit of trivia for a genuine appreciation of the immense forces that shape our world. The Earth's spin doesn't whisper its secrets in your sink. It shouts them across oceans and skies in the form of continent-sized storms. Now you know the real story. What other half-truths are still out there? If you enjoyed this episode, please subscribe, leave a comment, and join us next time. Until then, stay curious.